Wait, all right, we are recording. So any questions, any problems that anybody has any questions about?
I have a question about ALEKS.
Which ALEKS?
I don't know.
Homework ALEKS or the ALEKS that does the lab experiments?
No, just in general about the homework and the test. When I use the calculator, it like slows down everything.
It lags everything.
Like yeah, the timer on the test was like lagging, and it took like more than a few seconds to actually get an answer from the calculator.
What I would
I didn't have any other.
What I would recommend doing is just go ahead and pull out a scientific calculator and try to think. In the next exam, you probably don't need it. But if you ever had to do like molar mass calculations, just like have a periodic table right next to you.
Okay.
Or
is it better, do you think, to use like Internet Explorer over Chrome?
I have found that Chrome works better. In the past, I used to have a little bit of problem with Chrome, and I had moved, I think, to Mozilla.
Okay.
But I also use Safari on it. So I don't know if you have Safari. So I've used Chrome, Safari, and Mozilla. Those I think Internet Explorer has been replaced now, right? Isn't it like it's got some other name? It starts with an E, but
I don't know.
Or,
okay, I'll try that. Thank you.
What you might want to do is when you're doing the homework on it, play around with those browsers and see which one gives you the best response time. And I do tend to just kind of close as many windows from other applications and stuff as I can. And then just make sure you don't have Zoom running in the background somehow. You know, Zoom really takes a lot of, so sometimes I forget to turn it off when I'm doing something else.
Oh.
But okay, it could, I'll be honest with you, it could have just have been like the particular time you were doing it. And just like what the internet traffic happens to be like at that minute. So sometimes stuff runs faster for me and sometimes it runs slower. And I think it just has to do with like, I don't know, I'm in a building. So like everybody is sharing the same internet cable coming into the building, and that can have an effect on it too.
Yeah.
So yeah.
Okay,
but in terms of the calculator, I would use, I really don't like calculators. I mean, I'll use them once in a while if it's, I don't want to get up and get a calculator, but I find that you can do it so much faster. I can do it so much faster on a regular calculator. And so try it that way. Yeah. Because you're right. I mean, when you're on a timed exam, you want every second. Like every second is precious. Okay. Any other questions? Okay. All right, I'm going to mute everybody. If you have a question, just unmute yourself. Okay, so what I'm going to do today is I'm going to go over some of these, or at least a few of these problems from chapter 4. And the first one is, oh, by the way, just one more comment about the exam. So at some point this week, probably a little later this week, Thursday or Friday, I will start going through the exams and sort of regrading them because ALEKS does not give partial credit for any of the questions. So I'm going to go back and give partial credit. So one of the things that happens sometimes is like you might put an answer like 3.01 and ALEKS wants 3.0. And then it'll give you 0 for that one. So I have to fix that. Generally for sig figs, I only take 5% off. So you would get like 0.95 out of that, stuff like that. Sometimes there's multiple choice questions where you have to do 3 of them or 4 of them. And then if you get one of them wrong, it gives you a 0. So if there's 3 parts and you get 2 parts right, you get 2/3 credit. So I got to fix all that kind of stuff. It's kind of time consuming, but I will get to it on Thursday and Friday. So over time, you may see an adjustment. Your score may go up. Okay. Let's see here. So the first one that I wanted to look at, again, we're at chapter 4, and what I wanted to do was to talk about precipitation reactions. There's a couple of what I would call skills that we want to develop in terms of precipitation reactions. So the first one that I'm going to look at is called writing net ionic equations. Okay, so a precipitation reaction is a specific type of reaction. So for example, formation of bone. So bone, for example, has hydroxyapatite in it, which is not a simple substance. It's complicated. Apatite. It's a complicated substance, but it's essentially a mixture of calcium and phosphate ions in the form of a solid. So this is called calcium phosphate. Okay. And so the formation of calcium phosphate generally comes from calcium ions that are dissolved in water. So that's calcium, right? And phosphate ions, which are also dissolved in water. So remember, we put AQ to indicate that this ion is dissolved in water, and then you get a solid out of it. They combine. It's kind of cool. These ions will combine to form a solid, right? And the ratio is 3:2, 3 calciums to every 2 phosphates, because if you recall, calcium is a monatomic ion in group 2A, and all the ions in group 2A are +2. Phosphate is a polyatomic ion. Okay, I talked about that in the last lecture, and it has a charge of -3. So the driving force behind forming an ionic compound is that the total positive charge has got to balance the total negative charge. So by having 3 of these calcium ions, you get a total positive charge of +6. And by having 2 of these phosphate ions, you get a total negative charge of -6. And guess what? There's your balanced charge, right? That's what determines how many of these ions will combine with each other to form the ionic compound, all right? So in the first question, the first type of question of writing net ionic equations, what they do is they give you the balanced molecular equation. This is called a molecular equation. I'm going to need a little more room over here, so let me erase this. Okay, so the first compound in the reaction is called zinc chloride. It's combining with potassium sulfide. And then you get 2 products, zinc sulfide and potassium chloride. All right. Okay, so take a look at this. This is called a molecular equation, and you can recognize a molecular equation because it's kind of like the equations we've talked about in chapter 3. It's where you just show everything. You show a reactant and another reactant and a product, and you're showing the chemical formulas for the substances, right? So you've got zinc chloride. Remember, most of the reactions that we look at are reactions that involve binary compounds. A binary compound is a compound that has 2 parts. So not all compounds are binary compounds. There are very complicated compounds out there, but most of the ones we look at in general chemistry are binary, meaning they've got 2 parts. The zinc is 1 part, the chloride is the second part, 2 parts. The potassium is one part. The sulfide is the second part, 2 parts, binary compounds, right? And even on the product side, 2 parts, zinc and sulfide, potassium and chloride, 2 parts, binary ionic compounds. So if you can think of the, at least in terms of precipitation reactions, as each substance having 2 parts, that can kind of help you analyze what's happening. Now, what I want to show you is what happens essentially here is what's called double replacement. And that's an aspect of precipitation reactions, is double displacement. Sometimes the term is replacement, double replacement. But essentially what's happening is the first part of the first compound, so that's the zinc, is displacing the first part of the second compound. They're essentially switching partners. So the zinc starts with the chloride and the potassium starts with the sulfide, but in the end, the zinc is now with the sulfide and the potassium is with the chloride. That's a precipitation reaction. At least that's how we would represent it. Switching partners, okay? So sometimes you can just write like a little arrow, like see what's happening? The zinc is now combining with the sulfide. And the potassium is now combining with the chloride. That's the molecular equation to give you the 2 products, okay? This is a relatively simple one because the charges are pretty balanced, okay? Now, how do we write the net ionic equation? That's the goal here, is to write the net ionic equation. And there are different methods for doing this. So I'm just going to show you my method. Feel free to read ALEKS's method. Remember, every time you do an ALEKS problem, there's an opportunity to see an explanation. They're going to give you an explanation. You can YouTube different explanations. Textbooks have available, but I'm going to give you my method. So here's what I would do if I were looking at this equation. I would first decompose, meaning break up each compound into its what I would call constituent ions, the ions that it's made out of. And the way you'll go about doing that is, again, thinking of each compound as binary, having 2 parts. So if you look at this one, I'm going to decompose it into 2 parts. So you've got the zinc and you've got the chloride. So I'm going to put a plus sign in between to tell myself that I'm splitting it up into 2, okay? And then I'm not done yet because I'm going to go back and do the charges, but I'm first showing you just how to decompose. So then I'm going to decompose these into 2 ions. These are all ions. That's the nature of precipitation reactions. Oops, I made a mistake there. Potassium and sulfide, right? So potassium sulfide, zinc chloride. Then you have the arrow, and then you do this. Now here's what you're not going to do. See where it says solid there? That solid is called a precipitate. A solid is a precipitate in the chemical context. So what that means is the zinc sulfide does not break up into ions. It's a complete compound that does not dissolve into water, just like bone tissue doesn't dissolve into water. Technically, bone can dissolve, right? Because there are these enzymes that will, or these cells actually, that will dissolve the calcium phosphate in bone. But on its own, if those enzymes and if those cells didn't exist, it wouldn't do it. It would just sort of stay solid in water. Okay, so if it's a solid, you just bring it straight down. You don't decompose it. Okay, and I'm going to put solid there. Okay. Next thing, if it's aqueous, again, you decompose it, just like I did the first 2. So aqueous decompose, solid don't decompose. And then I'm going to go back and do the states of matter. And then make sure you put a plus sign. Every time something breaks up, you put a plus sign so that the plus sign represents that these are different substances, right? So if I say X plus Y, X is different than Y. They're different substances. X times Y would be a thing. So you're going to have those plus signs all over the place. Now I go back and do the charges, okay? This is where the discussion last week comes into play. Remember, some of the ions are in the periodic table. So for example, group 7A is -1, group 6A is -2, group 5A is -3, and then on the other side, group 1A is +1, and group 2A is +2. And then we had a couple of ions that we said you could just memorize. So aluminum is +3. I'm going to give you one more. Zinc is +2, and then one more. Silver is +1. Those are three very common metals when you do these types of problems. So if you can memorize those three, that'll help you. You won't have, it'll cut down the amount of calculations you have to do. Okay. So you could figure out the zinc is +2 without memorizing it. I'll show you how. Because chloride is in group 7A, that means it's -1. Okay, how many chlorides are there? Okay, so let me put minus there because it's in group 7A. How many of them are there? There's 2 of them. So that's -2, -1 times 2. That means the zinc has to be +2, the opposite of the negative. So that right there would tell you this has got to be +2. Or you could just memorize zinc, +2. So it saves you time if you memorize that one, but you can figure it out from the chloride. Now let's go on to the second compound. Potassium is in group 1A. That's where potassium is. So that means it's +1. So I just write a plus. Sulfide is in group 6A below oxygen. So that's -2. Okay. And then now you've got them on the right side because potassium is not going to change. For precipitation reactions, the charges never change. So if potassium is plus on the left side, it's also plus on the right side. And then chloride, same thing. If it's minus on the left side, it's minus on the right side. Okay, we're getting there. The next step is to just write in aqueous everywhere. Aqueous for anything that's a charged ion. So if you see a positive or a negative, it's aqueous. It's dissolved in water because ions dissolve in water. They form aqueous ions. So AQ, 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 right? Aqueous. The only one that's not aqueous is the one they told you is a precipitate, is a solid. And remember, that's the one you keep all by itself. This, by the way, is called the Ionic Equation. This whole thing that I wrote there. See how long it is? It's got 4 separate things on the left side and 3 on the right. That's called an ionic equation. And we're almost at the net ionic equation. We're so close. Now what you do to get the net ionic, there's one more step. Think of your mathematical tools. If I had 3 plus x equals 3 plus y, you could cancel the 3's and determine that x equals y. You can do the same thing for ionic equations. Anything that's the same on both sides, you can just cancel them. So if you look, both sides have Cl minus aqueous, and both sides have K plus aqueous. You can cancel them. What are you left with? You're left with zinc, sulfide, and then on the product side, zinc sulfide solid. There's your net ionic equation right there. You've got it. There's your answer. Okay. So here's my disclaimer on this one. This is one method for figuring it out, and I'm not going to claim this is the only method for figuring it out. So you can, figure out what method you want to use or use the ALEKS method. But to me, I like this method because this method covers any kind of question that you might receive in a future class. So like if you're taking, I don't know, if you're taking a pre-meds exam, the MCAT, or you're taking a pre-pharmacy exam, the PCAT, this method will allow you to kind of figure out anything that they might want to question you about, okay? One more piece of information in here, just terminology. The ions that you canceled, like the chloride and the potassium, those are the 2 ions that got canceled. Those are called spectator ions. So the spectator ions are the ones that you canceled in this process. Okay. I'm going to show you another one because practice makes perfect, and doing just one of these is not enough to fully kind of get the method down. Okay. So I'm going to save this little photo here, and then I'm going to bring up another screen and try a second one. Okay. Let's see here.
I have a question.
Yeah, go ahead.
What do we use the net ionic equation for?
So the net ionic equation is the way that chemists represent the actual change that occurred in the reaction. Because remember, chemical reactions change, right? So in this reaction, chloride and potassium actually didn't change. And that's why they're spectator ions. That's why we cancel them. The chloride at the beginning of the reaction is dissolved in the water. So is the potassium. At the end, they're also dissolved. So they didn't do anything. Whereas the zinc and the sulfide, these two ions right here, they actually reacted with each other to make a new substance. So when you buy, actually, take for example, the vaccinations that there are, you can now get for COVID. If you look, and you can find this information online because it's, it's stuff that the companies are patenting, so it's public information. You can look at what their formulations are, and what you'll find is that there are substances in the formulations that are spectator ions. They're in there. They essentially are part of one compound that's a reactant. And then after you inject it into the body and all of the chemistry and all the biochemistry occurs and all the molecular biology occurs, those ions are still dissolved in the water. They're dissolved in your bloodstream, right? But they don't do anything. So they're spectator ions. So the net ionic equation, what it does is you look at the molecular equation. There's all these substances in there, right? Which ones are actually doing the chemistry? You really have to kind of look pretty deeply to see, well, what happened, right? But the net ionic equation shows you what happened. This is the chemical reaction right there. The zinc combined with the sulfide to form the zinc sulfide. That's what the net ionic equation shows you. It cuts to the chase of what the reaction is. Not unfortunately, but in reality, you can't buy zinc ions. It's impossible to buy zinc ions because zinc ions are positively charged, so they're attracted to something else. So that means you have to buy zinc chloride and dissolve it into water. So this is the actual substance that you would add to water, but this is the actual reactant. So that's what it shows you.
Okay, got it.
That's a great question. Okay, let's look at another one. This one is going to be a little more involved because we're going to have a polyatomic ion in it. And it's going to involve a metal that we probably haven't seen. So let's try this one. But the form is the same. So SNCNO32, I have to be careful here. I haven't seen this compound. Na2S. Okay, so there's your reactants. So one of the things you'll want to do as you look at these problems is recognize kind of the form. There we go. See the form here? Again, you got a metal, which is part A, and you got a non-metal, which is part B. Binary ionic compound. A metal, there's part A, a non-metal, there's part B, right? So again, not all reactions are like that, but precipitation reactions are. It's always a binary compound with a binary compound to form two new binary compounds. And again, if you look at it, see what's happening. It's switching partners. The tin is starting off with the nitrate, and the sodium is starting with the sulfide. In the end, the tin is now with the sulfide, so it's combining with that second part. And in the end, the sodium is now with the nitrate, so it's combining with that one. That's essentially the form of a precipitation reaction. So you can see why we have that category, right? If something, like if you have all these like thousands of different types of reactions and they all kind of have the same form, oh yeah, the part A combines with the part B of the second reaction, then it's useful for us to classify it as a pattern that we observe. And so that's what's happening here. It's a double displacement or a double replacement. And it's a precipitation. And you recognize it's a precipitation, and here's the way. Aqueous, dissolved in water. Aqueous, dissolved in water. Solid, precipitate. Aqueous, dissolved in water. In fact, here's a little tip. The spectator ions are going to be the product that's aqueous. These are going to be spectator ions. Because this is a precipitation reaction, the reaction is forming the solid. So if the ions on the product side are aqueous, they're going to be spectator ions. You can kind of cut to that real quickly. So let's do what I did last time. I broke up each of the compounds that are aqueous into ions. I'm going to try to write these a little smaller because there's so many of them. Tin and nitrate. Now, here's something that people often make a mistake on. You got to recognize this is a polyatomic ion. If you have NO3 grouped together, nitrate, that's a polyatomic ion. So when you split everything up, don't split it up into nitrogens and oxygens. The polyatomic ion is a stable ion that stays stuck together, okay? Just like phosphate or acetate or hydroxide, they don't break up. So part one, part two. Same thing, and again, don't forget the plus signs, split them all up. Same thing with this one. You break it up into two parts because it's aqueous. This one's a solid. That's why we don't break it up. It doesn't dissolve into water. In fact, I can put solid right there. And then this one, it's aqueous, so break it up. Okay. I put the charge there, but I'm not ready to do the charges yet. I'm going to go back and do the charges in just a second. Okay. I think when I did the first one, the second time, the second thing I did was I put all the aqueuses in there. So we can do that. Aqueous, 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 aqueous. It seems tedious to do that, but it's important to do it because for a chemist, it's important to know whether something's dissolved in water or not. So if you don't put aqueous, it could be interpreted that it's a solid, like a metal, like tin's a metal, right? So it could be a solid. So you really want to put the aqueuses in there. Then you do the charges. Now here's the thing about tin. We don't have a rule for tin. I can't tell you it's in group 16A, so you're going to make it +2 or +3. You have to figure it out from context. Only the first two columns, and then zinc, silver, and aluminum, those are the only ones you can tell just by where they are in the periodic table. So here's how you do the zinc. You come back to the polyatomic ion and you figure it out from context. Nitrate is one of those polyatomic ions that you want to memorize or at least put on a list. It's -1. Okay, that's called the nitrate ion. Okay. How many are there? There's 2. Right? Remember that 2 means that there's 2 of whatever's in the parentheses. So that's -2. The metal has to be the opposite of that. So the tin has to be +2, right? So you figure out what the negative is and then figure out the positive from it. It's got to be equal. So +2. Again, nitrate's -1. So you can just put a minus. Sodium is in group 1A, so plus. Sulfur is in group 6A, so it's -2. And then you've got the charges already here, because whatever they are on the left, they are on the right. When we look at redox chemistry, we'll see that the charge can change from reactant to product. That makes it different. But for precipitation reactions, whatever the charge is on the left, it'll be the same on the right. Okay? So those are all the charges, right? Again, here's the terminology. Molecular. That shows the whole formulas. Ionic, that shows all the separated ions. And then we want to get the net ionic. Okay, so the third one is net ionic. So how do we do that? Just cancel everything that's the same on both sides, the spectator ions. So here's what I mean by that. You have tin +2 aqueous. So look at the symbol. the charge and the state of matter. If it's the same on both sides, you can cancel it. It's not the same for tin though, right? Here, it's not a separate ion. It's not Sn plus 2 aqueous. It's SNS. That's different. So you can't cancel the tin. Nitrate, NO3 minus aqueous. NO3 minus aqueous. That you can cancel. Wham. So those are gone. Those are spectator ions, right? The nitrate is a spectator ion. So again, when you buy a medicine that's a solid, the spectator ions are precipitated as a solid, but when you ingest it, so for example, I'm trying to think like what would be an example. Not like aspirin. Aspirin is like a pure substance. Sometimes they'll put some fillers in there, but really like, you know, real pharmaceutical drugs that you would take, like Lipitor, for example, or I don't know, you know, any of the things that you need a prescription for, they're really formulations. They're mixtures of different compounds. And so when you ingest it and it goes into your stomach, some of those compounds are soluble in acidic environments. So the acidity of your stomach will cause those spectator ions to just dissolve into the stomach. Okay, so the sodium ion, it's identical on both sides. Okay, so what are you left with? You kind of know, if you look at the molecular, you can tell what you're left with. If it's a precipitation reaction, we're looking for this. We're looking for that solid. So that tells you right there, we're probably not going to cancel the sulfide or the tin. But what you do is you just look at what's left over. You've got tin, you've got sulfide. Those are the two ions that are going to make the solid. So you just copy them down. Sn plus 2 aqueous, S minus 2 aqueous, and then SNS, solid. There's your net ionic equation. And just, you know, look, to me, it's a little annoying about people that do computer programming. And I guess if you, depending on who you would talk to, some people are more, they find this more important. The convention in chemistry is that when you write the charge, you write the number, then the sign, okay? So typically it's written this way. You put the 2 before the plus. You put the 2 before the negative. If you do that on ALEKS, it's much less likely to bother you and say, do it again. To be honest with you, it means the same thing. Plus 2 and 2 plus is the same. And in the old days, back when I started chemistry, before they even had, before professors even had computers, you would actually, they would write the exams like this. They would write Sn plus plus, and they would write S minus minus. Why? Because that means plus 2 and minus 2, right? 2 negatives is minus 2, 2 positive. And the reason they would do it that way is because it was just easier using a typewriter to do it that way than it was to actually put 2 plus, just because of the nature of the way the typewriters were designed. So in a sense, it doesn't matter. You could put plus plus, or you could put 2 plus, or you could put plus 2. But again, you're kind of limited by the software. So make it easier on yourself and put the number and then the charge, and then it probably won't bother you as much. Okay, so there's a second example of that type of problem. Do you have any questions about that? It's, you know, there's quite a few steps in there.
I'm sorry, Professor, quick question. You said that one is 2 plus, right? You have to do it on ALEKS, not the S plus plus, S minus minus.
Yeah, right? That's just an old style. This is from, you know, the 1970s. Don't worry about that. Ancient history, right? So
thank you.
Yeah. Things change over time, like the way we represent information changes over time. And so sometimes what you'll see as a student is you'll have an instructor who might be using an older system and hasn't switched over to the newer system. There's all kinds of things that change, like just a few years ago, the physicists just changed the way mass is even defined and the way time is defined and all that, but it hasn't worked its way into our textbooks yet. So things change over time. So when you're tutoring people 10 years from now, you'll see that they have different information than you remember. Okay, so that's the writing of the net ionic equations. I want to show you the second type of precipitation problem, and it's called predicting precipitation. Okay, predicting precipitation. So in this particular problem, what they're going to have you do is fill out a table. So they're going to give you the name of one type of compound, which is your first reactant. So I'm going to write it just because I'm not on landscape, I'm on the opposite of landscape. I forget what it is, portrait. I'm going to write it this way. So your first that's your reactant, and potassium sulfide. And then the solution B is zinc bromide. Okay. And then the question is, do you get a precipitate? Is there a precipitate? All right, PPT question mark, meaning is there a precipitate? And then you're just going to select yes or no. Okay. And then the last column is what's the empirical formula of the precipitate. Okay. So then you're going to fill that out. The formula, not the name, okay? So if you take a look at this, and there's 3 of them that they have you do, so I'll show you the other 2 after we do the first one. There's some skill here in terms of the naming of the compounds. So I want to show you how to do that. So essentially what we're trying to do, remember the whole idea of a precipitation reaction is that you have something that's dissolved in water that is, actually, let me use an M. That is, like a metal. Potassium is a metal, sodium is a metal. And it's going to combine with something, a non-metal. So I'll write N for non-metal, that's negative. And those ions, when they collide with remember, they're all bouncing around in the water. Ions, like, when you dissolve salt in the water, there's all these ions bouncing around in there. Boom, they hit each other, they form a solid. Falls out of water, right? So you're getting a solid. Oop, Mn. That's your precipitate, right? So when they say the empirical formula of the precipitate, they mean this, write the formula down there. Okay, so it's actually not that hard. But you have to use what are called the solubility guidelines. Okay, so there are solubility guidelines in ALEKS. There's also solubility guidelines in your textbook. In your textbook, they're table 4.2 and 4.3. Okay, there's 2 little tables there. One's on one page, one's on the next page, okay? So I'm going to give you not all of them right here because you can just use those tables. You can just look them up, but I'm going to give you a couple of them. So the first one are the highly soluble compounds. This is table 4.2. And again, I'm just going to give you a couple of them because, you don't need to see them all right now, but you can look them up. So the highly soluble, these are ones that will always dissolve in water as long as there's enough water to dissolve it. So group 1 metals. So that is lithium, sodium, potassium, rubidium, and cesium. Okay, any compound that has that ion, any of those ions, they dissolve in water. They will not form a precipitate. There's one more in that group, ammonium. These will not form a precipitate. They will not get a solid. They won't form a solid. They always dissolve in water. So that's why formulations for drugs often have sodium salts or potassium salts. It's because they want it to dissolve. So how do you make something dissolve? You attach sodium to it. You attach potassium to it. That ensures that it will dissolve. You can't use lead. Lead doesn't work because lead sometimes precipitates. There's other reasons you don't want to use lead, but that would be one, is that it sometimes precipitates. So you want to find something, if you want something to dissolve, attach a sodium to it. Well, if you can't attach sodium because someone doesn't, they have hypertension and sodium can be bad for them, then you attach another metal like potassium to it, okay? Some other ones. Some of the polyatomic ions, if they have nitrate, okay, this is called nitrate. Let me write it in parentheses. Any compound that has nitrate will dissolve in water no matter what. Acetate. And then there's one more, chlorate. I wrote it the wrong way. Sorry. Chlorate. Okay. Again, all of these will not form precipitate. Okay. They dissolve no matter what. They're soluble. Okay. Now, there are some that do form solids. They generally do. Again, there's others. I'm just giving you the kind of the bare bones minimum ones right there. You look at those tables to see all of them. There are some that form solids. Again, in water. We're talking about in water. Okay, so which ones form water? Well, actually, the first one are the sulfides. These are the sulfides. They almost always form solids. The phosphates. The carbonates. You can see why bone is made out of phosphate. There's one reason that bone is made out of phosphate. You don't want your bone to dissolve unless you want your bone to dissolve, right? But in general, you don't want it to dissolve. So you make it out of phosphate, but you don't make it out of nitrate. Bones are not made out of nitrate because you make them out of nitrate, they're just going to dissolve. So there's an evolutionary reason why phosphate is part of bone tissue. Of course, it's also convenient because it's used in all the metabolism aspect, right? So carbonate. And there's others as well, but for now, if another one comes up, we'll look at those. Okay. Let's see. So these ones, they will precipitate. These ones will precipitate. Now here's what happens. You may have a contradiction here, meaning I told you that sodium never precipitates, but sulfide always precipitates. What happens if the two are together? What if I have lithium sulfide? One precipitates, the other one doesn't. How does that work? The way it resolves itself is these ones always take precedent over these ones. So priority is with these ones. So if you have, for example, lithium with phosphate, it will not precipitate. If you have cesium with carbonate, it will not precipitate. So you always pick these ones up here first. That one, if there's a contradiction. Often there's not a contradiction, okay? Let me give you one more sort of in between. So it's the halides, group 7A. So that's chloride, bromide, and iodide. They don't precipitate unless they're with 3 specific ions. This is like a famous rule, so I do want you to know this one. If they're with lead, silver, Ag, sorry, or mercury. Okay. In this case, they form a precipitate. Okay. Most likely when you do these ALEKS problems, you're going to get one of those because it's such a famous example. So really, in a sense, I broke it up into 3 categories. Never precipitate, always precipitate, usually don't precipitate unless they're with one of these 3. Okay. So again, there are some other rules, but these are the most important ones. And these are probably like 75 to 80%. You just look at those 2 tables, table 4.2 and 4.3, and you'll get the other ones in there. Okay. So what is this problem asking you to do? It's really asking you to figure out what ions are in these 2 compounds, switch the partners, and then see if one of them forms a precipitate. And the way you figure out whether it forms a precipitate is which category it's in here. If it's in this category, no precipitate. If it's in this category, yes, precipitate. If it's in this category, no or yes, depending on whether there's silver, lead, or mercury. Okay, so what I'm going to do, I want you to have these here as I work through this problem. So here's what I'm going to do first. I'm going to convert these to formulas. Okay, so potassium. You pull out your periodic table and you look up potassium and you find that it's K. Right? And then sulfide. Well, you pull out your periodic table and you know that that's S. Then you get the charges. Potassium is in group 1, so it's K+. Sulfide is in group 6A, so it's -2. Remember, I'll put -2 there. Okay. So what I would recommend when you do these problems, you don't really have to write the formula properly on the left side, because you're just going to figure out which compounds form on the right side. So you can, you could figure, oh yeah, it's K2S. You could do that, but you don't really need to for this one. Same thing here. Zinc, remember that's one I said to memorize, +2. So zinc 2+. And then bromide, group 7A. If it's in group 7A, it's -1. Okay. Now, those are the 2 ions for each compound, compound A and B. Switch partners, right? Precipitation is switch partners. So potassium goes with bromide, and zinc goes with sulfide. Okay. So now what I'm going to do on the right side is I'm going to write those 2 formulas down. KBr. That's an empirical formula, okay? When you write ionic compound formulas, those are called empirical formulas. Zinc sulfide, ZNS. Got that one too, right? Now you use your solubility guidelines. What you do is you look, okay, first compound, potassium. That's right here, always soluble. Always soluble means no precipitate. Okay, so that is not going to be the formula for the compound that forms a precipitate. Let's look at the second one. Okay, zinc. Is there any rule for zinc? No, there's generally no rules for zinc, but there is a rule for sulfide. Sulfide, always soluble. I'm sorry, always precipitate, right? It's that second category, always forms a salt, unless it's with one of these metals. And it's not with one of those metals, it's with a different metal, it's with zinc. So that means it's a precipitate. So now you can say, yes, we do have a precipitate here. And then you can say, what's the empirical formula? Here it is, ZNS. There's your formula, okay? So write the ions, switch the partners, and then use the solubility guidelines to determine whether it's going to form a precipitate or not. Okay. Let me show you a second one. I think, yeah, we have 10 minutes, so we've got enough time for 3. Okay. Okay, I'm going to have to show you a couple of other rules, but that's fine. So let me get rid of, actually, let me just go ahead and save that. Let's do a different one. So the first one, solution A, is sodium hydroxide. B is copper 2 sulfate. And then you're going to do yes or no. And then the empirical formula. Okay. All right, so here's what we're going to do. We do, okay, sodium. Sodium's in group 1A. That means it's +1. Okay, hydroxide. Remember, hydroxide is one of the polyatomic ions that we talked about last week. It's a very common polyatomic ion. Its hydroxide is OH minus. Sodium hydroxide, okay? Second one. Now, when you have a transition metal and they give you the Roman numerals, that's the charge right there. So if it says copper 2, that means it's +2. So copper, be careful with copper. Cobalt is CO. Copper is Cu, and it's just Latin, right? So cuprum is the name of copper. In fact, the last name Cooper, when people have the name Cooper, that generally means that somewhere back in their family heritage, they probably worked with copper. So certain people are named after copper. So, or at least I've heard that. Sometimes those things are not true, but so Cu. The Roman numerals tells you the charge. Okay. And then sulfate is a polyatomic ion. So SO4, you look that one up or you memorize it, and there you go. Okay. Switch partners. So the copper 2 is going to combine with hydroxide, and the sodium is going to combine with the sulfate. Now, they did a little trick here. It's not a trick, but it's something that happens. This is +1, this is -1. But this is +2 and this is -2. So what happens? What happens is if they don't have the same charge, they're not going to combine 1 to 1. So here's how you deal with it. Let's do the first one, sodium sulfate. NaSO4. This is +1, this is -2. So we need 2 of the sodiums to give us +2, right? If you have -2, you need +2. So you need 2 of the sodiums. So it's Na2SO4. For the copper, it's +2 and the hydroxide's -1. So remember, you write the metal first, then the nonmetal. But since this one's -1 and this one's +2, we need 2 of the -1s. So if it's a polyatomic ion, you got to write the parentheses as well. Okay. So there's your formulas. Now we need to determine based on the solubility guidelines. Okay, so let me rewrite some of those rules again, some of those guidelines. Always soluble. Remember, always soluble means no precipitate, okay? Li plus, Na plus, this is group 1. K plus, Rb plus, Cs plus, NH4 plus, always soluble. NO3 minus, acetate C2H3O2 minus, and chlorate ClO4 minus. Okay, so those are the ones that are always soluble. And then you have the ones that are precipitate always. Okay, so those are the sulfides, phosphate, carbonate, and I'm going to add one more, which is hydroxide. I forgot to put hydroxide. That's one of them that also forms a solid. That one also forms a precipitate. And then the third category was the soluble except with. And so those are the chlorides, bromides, and iodides, except with lead, mercury, and silver. So if they're with one of these, then they're a precipitate. But if they're not with one of those, they're soluble. So let's take a look. We got sodium, always soluble. So this is definitely going to be aqueous. So that's not a precipitate. If it's aqueous, it's not a precipitate. Copper, we don't have a rule for copper, but we have a rule for hydroxide. Hydroxide's in this category right there, precipitate. So there we go. We got our formula. So it does form a precipitate. Okay. So you got to go, yeah, you got to go through all these steps. It's a lot of steps in that. But once you do a few, you'll get quick at them. So let's try one more. We got one more, and we got about 5 minutes or 4 minutes. So let me, I'm just going to erase this here. And we'll use the same space here, because I want you to see the solubility guidelines. Okay, third one is nickel 2 sulfate. And it's going to react with magnesium 2 iodide. Manganese. Okay, one thing to comment on that, a common mistake for people is to get these two elements confused. Magnesium. That's what you need in your diet, right? The other element that sounds the same is manganese, and this is Mn. This is a transition metal. Okay, so be careful about that because they're different metals and they have different solubility properties, okay? Okay, so let's go through it. We got nickel 2. Nickel is Ni, and they're telling you it's +2. Sulfate is a polyatomic ion, which is a charge of -2. Manganese 2. Remember the Roman numeral, that tells you the charge of the metal. So it's Mn +2. It's kind of cool. If it says manganese 2, you know the charge is 2. If it said manganese 4, you would say the charge is +4. And then you got iodide. Iodide is in group 7A, so it's -1. Switch partners. Okay. Now, it looks like these two are balanced in terms of their charge. One's the same as the other, +2, -2. So that's cool. If they have the same charge, you just write them just as they are. So our formulas here would be MnSO4, right? +2, -2, so it's 1 to 1. But the nickel's +2 and the iodide is -1, so we need 2 iodides.
How do you know which one to write first?
You always write the metal first. So the metals are the first 2 columns, and then the whole middle part. Think of it geographically. The 2 metals on the left are kind of like the west coast of the United States. Then you've got the whole Midwest and the desert and all that, the plains, that's the transition metals. And then you get all the way over to the right, that's like the East Coast. The East Coast are the non-metals, okay? So non-metal, non-metal, okay? When they give you the name, they're gonna put it in the form of metal, non-metal. So it's already kind of, you know, it's already in the order that you need to write the formula. Okay, so again, 2 iodides to give us the charge of -2 to balance the +2. Then we just go to our solubility guidelines. Okay. Now, it looks to me as though, well, we can definitely do the nickel iodide because here's our rule. It's always soluble unless it's with one of these, then it's a precipitate. Well, nickel is not one of those 3, so it's going to be soluble. So this is aqueous. Okay. Now, what about the manganese sulfate? There is no guideline. I didn't give you one for that one. Okay, so that's my point about how I didn't write them all down because I didn't want to write them all down. So you go to table 2 and you go to table 3, and there's going to be another rule about sulfate. And sulfate is sort of like the chlorides and bromides and iodides. And what I mean by that is this. It'll tell you that sulfates are generally soluble, except with, and then they give you some ions that are not soluble. And so that includes silver, mercury, lead, just like the chlorides, bromides, and iodides. But there's a couple of others too. So Mg is an example, and calcium is an example. So it's also not soluble with those ones, but it should be soluble with everything else. As long as it's not in this little list here, it should be soluble. So you come over here, oh, manganese. Careful, magnesium is not the same as manganese. So it's not in this little sort of exception list. So that means it's also soluble. So that means it's aqueous. Now, what we would do is we would say, hey, we figured out from these solubility guidelines that both these compounds are soluble. They do not form a precipitate. So there is no precipitate formed. And so there is no empirical formula to write, right? They only want the empirical formula if it forms the precipitate. So what that means is if you dissolved these compounds into water, what they would do is they would dissolve into ions. So that's fine, they'll dissolve. But they won't do anything. They won't react with each other. They'll just stay dissolved in water. It'd be like you dissolve some sugar into water, you dissolve some salt into water, but nothing would happen. They would just be dissolved in the water. So there is no precipitate form. There's no empirical formula to figure out. You're done. There you go. Okay. So you, in a sense, you have kind of two options here. You're either going to get one of the compounds forming a precipitate, or you're not going to get any precipitate at all. Okay, so one precipitate or no. There's like one kind of reaction where you get two precipitates, but you don't need to worry about that one. Okay, so practice those, and then that's all you really have to do for chapter 4.2, for section 4.2. You have to do this type of problem and then writing the net ionic equations. So just kind of, allot out your time for that section as, okay, I'm going to learn how to do these two types of problems and practice each of those two. And then tomorrow, what we'll do, if you want to go over one more tomorrow, we can do that if you have a question about it. But otherwise, what we'll do is we'll start talking about acid-base reactions, which is section 4.3. And then on Wednesday, we'll start working on redox chemistry. And then on Thursday, we'll do the molarity. We'll do the molarity calculations on Thursday. And then that'll be it. Okay. Let's see. I'm sorry, let me pull. Yes, I do have time. So what I'll do is I will end the session and then upload the recording. But if you want to meet me after class, just give it maybe 3 or 4 minutes and I'll restart the Zoom and then we can meet then. Okay. Awesome. All right, you guys, have a great day. And if you have questions, let me know this today. And otherwise, I'll see you tomorrow.
Thank you.
Thank you.
Bye-bye.
Thank you.